Okay, let's proceed now by analyzing the two new control volumes in this Rankine cycle with regenerative feed water heater. The first new looking control volume is the open feed water heater. I say this is new, however, this looks quite similar to sample exam problems from the second exam, after which we covered open control volume systems. So we have all the tools here. I'm going to draw just a box to indicate my open feed water heater, and surprise, surprise, I'm going to identify the boundary. I'm going to identify that this is an open system, control volume, and I need to label interactions between the system and the surroundings. This is going to take the form of mass flow in and out. I have state 2, mass flow rate at state 2. Coming in, I also have what is state 5, mass flow rate at state 5. And then exiting, I have what I'm calling state 6, mass flow rate at state 6. I'm just copying this from my previous diagram. I'm going to make some of the usual assumptions. So steady state operation, one-dimensional flow, uniform state, so the properties don't vary across inlets. And I'm going to have negligible heat transfer. Again, this is between the system and the surroundings. So the heat transfer, the energy exchange is occurring inside the control volume. So I have negligible heat transfer between my control volume and the surroundings. Negligible work, there's no moving parts. And also negligible changes in kinetic energy and potential energy. Okay, let's apply our tools. If we wanted to, you could reference the first law flowchart to help analyze this control volume. The first thing we could apply would be the conservation of mass. And we actually just did that. Mass flow rate coming in, state 2, must equal mass flow rate going out. There we go. Let's divide by the total mass flow rate. And actually what I'll do is I'll go back. You should be able to realize, looking at the previous slide, that mass flow rate at state 6 is the same thing as mass flow rate at state 1. It's the same loop. Also, the mass flow rate at state 5 is the same thing as the mass flow rate at state 3. It's the same branch of that loop. And we've got mass flow rate of state 2 here. Okay, so putting all of those pieces together, I have mass flow rate of state 1 equals mass flow rate 2 plus mass flow rate 3. And I can let the fraction be defined as mass flow rate 2 over mass flow rate 1. Then that must equal 1 minus y. Okay. Next, let's apply conservation of energy, the first law. on my control volume. If I do that, I have 0 equals rate of heat transfer, rate of work, the sum of the energy that's being brought into the control volume by incoming fluid streams. And that can take the form of enthalpy, which is the combination of internal energy to fluid and the flow work. I have kinetic energy, potential energy, and then I need to subtract energy being carried by the fluid as it leaves the control volume. Okay, let's apply my assumptions. I said negligible heat transfer, negligible work, no moving parts. This device is not intended to change the velocity of the fluids. That's not its purpose. Changes in kinetic energy are going to be negligible, and the same thing about changes in potential energy. So let's see, I've got 0 equals coming in. I have 2 fluid streams. Let's look at state 2. So I have the mass flow rate at state 2 times the enthalpy at state 2. I have the mass flow rate at state 5 times the enthalpy at state 5. Leaving, I have the mass flow rate at at 6 times the enthalpy at state 6. And again, to try to simplify things, I'm going to realize that the mass flow rate at state 5 is the same thing as the mass flow rate at state 3. And the mass flow rate at state 6 is the same loop as the mass flow rate at state 1. Again, if you need to convince yourself of this, look at the previous slide and just trace it, and you'll see those are the same flow rates. Okay, let's try to simplify a little bit. Let's divide everything by the mass flow rate at state 1. Let's do that to both. Well, I have to do that to both sides by the laws of algebra. So I have 0 equals m dot 2 over m dot 1 times h2 plus m dot 3 over m dot 1 times h5 minus h6. Okay, and furthermore, the fraction m dot 2 over m dot 1 is my definition of y. It's the fraction of fluid that's bled off after my first turbine. And then the second fraction is 1 minus y, according to my conservation of mass. And at this point, I can solve for y explicitly. Just algebraically, I end up with the relationship h5 minus h6 divided by h2 minus h5. Okay, so applying the first law on the control volume of the open feed water heater gives me a relationship between the state enthalpies and y, the fraction of fluid that's bled off after the first turbine. And we'll keep that in our pocket here for later on when we analyze the total cycle.